I think I'm the last barrier between you and the happy hour, so I'll keep this as brief and simple as possible. I got an invitation saying that the title of this, or the theme of this meeting is about graphs, and it seems that I perhaps am the only one who took that seriously. So today I'm going to share a little bit about my other hot takes on whether we should be treating, or pretending that molecules are graphs. So these are from two papers that we've published recently. One on just the different functional forms that we choose in molecular mechanics force fields, and the other on the fundamental graph neural network architectures that we deploy on all of these many-body system modeling. Right, so here's a little sort of motivational slide that I sort of added to all of my talks. So why am I doing this? So fundamentally, I'm interested in developing methodologies that can accelerate the decision-making processes in drug discovery. So why are we doing this? There are a lot of targets out there that have been identified as proteins that might cause diseases or play a role in a disease pathway. And there are simply too many of them. And we are only making drugs that target them very, very slowly. So each year there are a handful of drugs being made, although there are thousands or hundreds of targets. And most of these drugs are repetitive in terms of the targets. And each of these approved drugs are being more and more expensive to design. And lastly, we're graduating fewer and fewer human chemists and biologists to actually design these drugs. So I'm interested in using machine learning methods and physics-based methods to help facilitate the decision-making process in this loop so that we need fewer humans and just more algorithms, which are cheaper. So these are two classes of distributions that if we are able to characterize for many systems, then we should have no problem whatsoever in computational design cures for a lot of diseases. So the first is the Boltzmann distribution, prescribed, conditioned on the graph, which just describes the energy landscape or how the atoms are distributed according to some energy landscape. And the second is the simpler Bayesian predicted posterior, which, based on data, tells us what's our belief about some property of some graphs representing the molecule. And the status quo of understanding these two kinds of distributions are not great. So for the physics-based or the Boltzmann distribution, we rely on force fields that are either very fast or very accurate, but never both. And for the Bayesian approach, or in general for the pure machine learning approach, we rely on architectures that are borrowed from other fields like social modeling. And they are not particularly suited for this kind of small, noisy data, graph-structured data that are typical in drug discovery. So I'm interested in making these two guys talk to each other to have machine learning to have machine learning inspired force field and sampling methods, and retrospectively or reciprocally have physicochemical prior to guide the design of machine learning methods. Right. So the second part, I think, for this audience is sort of very clear. But why do we need Boltzmann distribution, or why do we need to understand Boltzmann distribution? So it can be argued that all of the computational structural biologists' goal is to characterize Boltzmann distribution so that we can have a bridge between the macroscopic world and the microscopic world. So Mark Tarkman was here, and I believe this was one of the opening paragraphs in his textbook. So people sometimes make this assumption that if we only look at the minima of a Boltzmann distribution, we might also be able to deduce something regarding the system, but this is not that reliable. But it is very hard to understand Boltzmann distribution for any systems of any complexity, for any system that's more complicated than a hydrogen gas. So what we do instead is that since we do not have access to the true energy U here, we put a little hat on it and have a force field. And we believe that this force field is as close to the true energy or potential energy as possible. But again, the status quo is that on the one hand, we have the quantum mechanics-based methods, which are believed to be the gold standard, but they're extremely expensive to simulate, and they scale more than cubically with regard to the size of the system. So it can't really be applied on things like proteins. And on the other hand, we have this other kind of models called molecular mechanics, which are a much simplified version where we have a connected graph among the atoms, so that we put a very strong prior on the energy landscape regarding the system, and we assume that it never touches any space outside this prior. Right. So machine learning force field is a class of model that tries to reach the sweet corner where the dream is that we hope to have a model that's as accurate as a quantum mechanics-based simulation, as fast as a molecular mechanics force field. So let's start from the graph-centric approximation or abstraction and see what's wrong with all of our methods here. So the structural biologists, they simplify the molecule graph as just a simple graph connected by these chemical bonds. And all of the energy terms that they use in the simplified free energy model or potential energy model are simple objects that you can find in your local gym. So all of the chemical bonds are simply a little string or a harmonic term, and the same for the angle terms, and the torsion terms, just a very few terms of Fourier expansion or Fourier series that resembles a twist trainer. So of course, this is extremely chaotic and simplified, but I spent my PhD trying to improve this by having a graph neural network that reflects that respects the symmetry among these entities and parameterize end-to-end this force field so that we can be as accurate as possible while still keeping the simplicity. So this has many sort of interesting applications. So we can reproduce the quantum mechanics minima rather accurately. We can reproduce the NMR coupling rather accurately, and we can sort of predict a little bit of the binding free energy that we observe in wet labs. But of course, this is, and by the way, we use this in some very interesting applications. For example, in discovering or helping discover an inhibitor for a protein that might cause your heart and your hand-foot to display some abnormality. But still, this is even to the limit of a graph parameterized force field. This is still hugely inaccurate. So in our review paper, we plotted one of the best force fields out there, which is the OpenFF. We plot its energy and forces with regard to a quantum mechanics free energy landscape or potential energy landscape, and there is almost no correlation whatsoever. So this tells us that this graph approximation is a very crude one and perhaps not an appropriate one. So why are all of the computational chemists and computational biophysicists out there are still using this force field? Well, the only sort of comforting evidence is that this is very good at approximating the minima of the QM energy landscape. But in terms of the actual the value of the energies, it's almost completely wrong. Right. So the algebra based on spherical harmonics is a common suspect that people go to when they try to use a equivariant machine learning model to approximate more accurately the quantum mechanical free energy landscape. But of course, this is extremely expensive to compute and complicated and very hard to engineer. And another thing that we did was that we tried to use a simplification of this, and this is actually based on a special case of Soledad's talk yesterday, which shows that all of the OD or orthogonal group invariant scalar function can be written just as a function of the scalar products. So we use the even simpler version of that and only rely on the diagonal entries, and this is already doing a good job of approximating a lot of the properties as well as energies that we care about. And by the way, this is a lot easier for downstream applications. For example, this particular one I think is interesting because, So there were a lot of astrophysicists here, but this is actually an astrochemistry application. So we took one of our neural network architectures and we used it to predict the IR spectra. And some astrochemists use this to predict the component of atmospheric composition of some distant planet. Right. So what should we do with all of this, right? So we believe in our review paper that the next step or the future of molecular dynamic simulation should lie somewhere between the spectrum, between the fully sophisticated spherical harmonics-based machine learning force field and a simple crude graph-based assumption. And of course, we have a rich mathematical toolbox, for example, the one provided by Soledad yesterday, that can help us achieve this goal. However, all of these methods and all of these neural network architectures that composed of our force field, they all rely on this architecture that we borrowed from social modeling, which is this graph convolutional network. And I think this is true for pretty much all of the neural network modeling of many-body physics systems. But we never actually questioned whether this is a good assumption or not, right? We use this architecture and we use this convolutional operator over and over again on our n-body graphs without even thinking whether this is an appropriate inductive bias for physics-based applications. So last year, Kyung Cho and I wrote a paper on a brand new graph neural network, completely devoid of a graph convolutional operator called non-convolutional graph neural network. So at no point in this entire architecture did we even call the summation or average among nodes. And we showed that this works just as well, and this actually theoretically and empirically alleviate a lot of the problems from the inability to distinguish a lot of the graph motifs, which I believe somebody talked about earlier this morning. It can go deep without showing any symptoms. It's even faster, and it's very robust to perturbation of the graph. But before we look at this, let's think about why are we doing this? So graph convolutions are characterized just by the graph Laplacian. So this is the only unique thing on the graph manifold, right? So this is perhaps one of the simplest expression of a GNN, and the activation linear transformation, we have it everywhere. But the only unique thing is that we left multiply a Laplace, or left multiply the adjacency matrix of a graph. So if we don't look at anything else and only look at this left multiplication, then this is just a simple Laplacian smoothing, which if you apply over and over again, what it does effectively is that it's averaging your graph towards a shape that's uniformly distributed among nodes, right? So let's say this is a chemical graph or a physical graph, which is just water, and you're going to average your carbon and oxygen atom over and over again until it reaches some sort of equilibrium, where you have two-thirds of the carbon and one-third of oxygen for every node. And this sounds ridiculous, but this is the inductive bias that we encode in all of our GNN models. And quantitatively, you can characterize this phenomena by the Dirichlet energy, which is just the dissimilarity measure among nodes. And you'll see that as the number of layers go up, the difference among all the nodes will go down exponentially. So this is the reason why none of your GNN models can go very deep, because all of your nodes will look exactly the same. By the way, this is true for any graphs, not just physical graphs. So for social graphs, if you apply these Laplacian transformations over and over again, you will see that all the embedding lie on very thin space of the subspace. So all of your node will become just one node, which of course is pretty bad, but it's especially bad because of other reasons. One of which is this over-squashing phenomena. So this is also unique to GNNs. So if you take the derivative of an embedding with regard to that of its neighbor, you will see that this decays, again, combinatorially with regard to the depth. So what ends up happening is that you'll have a lot of information being squashed onto a fixed dimensional space so that you will lose a lot of information, and it is mathematically impossible under finite dimension or finite width of a neural network to encode a reasonably sized neighborhood just because of the combinatorial nature. So this is the this is a small toy graph, and it shows that if you wanted to encode a reasonable neighborhood of around 10 walks, it requires a few hundreds of dimensions. Right, so the last limitation of GNNs, which is also my favorite, is this limitation in the expressiveness. So no Weisfeld-Lehmann equivalent GNN can distinguish these two graphs. So the first graph is two triangles not connected, and the second graph is a 6 nodes all connected. Right? So if your GNN is Weisfeld-Lehmann equivalent, which a lot of your GNNs are, the expressiveness of that model is simply equivalent to a tree expansion. So no matter which node you start with, you're going to just expand your graph as a binary tree of all blue nodes. So it is impossible for a GNN to realize or to distinguish between these two graphs. So all of these originated from this assumption of homophily, which is the cornerstone of convolutional graph neural networks. So this is the very first graph published in 1977 on which people started to play graph modeling techniques with. And it's a karate club social network where people who are connected are more likely to join the same club. So this assumption is also known as birds of the same feather fly together. In other words, the structure connectivity and the semantic similarity imply each other. So one of the reasons why GNNs are especially limited in physical modeling is that this assumption is fundamentally wrong in physics, right? So on the one hand, you have two people. They may become friends or colleagues because they are similar in some measure. They have the same job, same hobby, same personality, etc. But in physics modeling, the inductive bias or the assumption sometimes is that they are attracted to each other precisely because they're different. Right. So what we proposed instead was this alternative form of modeling graphs, which is based upon unbiased random walk. So we relied on this very old mathematical formulation called anonymous experiment, which is the way to distinguish different random walks. So the anonymous experiment is a very simple characterization of the number of unique nodes insofar traversed in the first time it is traversed. So it sounds a bit mouthful, but it's as simple as this. So if you have a ring and you traversed this ring in a random walk, and by the time you reach the origin, you will label it 0. And if you have a linear random walk, you simply enumerate the integers. So for example, if you have a linear walk here without any repetitive nodes, you will just label this walk as 0, 1, 2, 3. And if you have a sort of a cyclic random walk, you'll label it 0, 1, 2, 0. So the first time it is traversed is 0th time, so you reuse that label. So this simple trick, it turns out theoretically that it can be applied on graphs and distinguish any non-isomorphic graph up to the reconstruction injecture. So this is a very powerful expression. So we combine this structure trajectory based on an anonymous experiment with our semantic trajectory, and we ended up with a GNN that are theoretically and empirically very expressive. So by the way, we wrap everything around the RNN so that we can process it. Right, so there are some theoretical guarantees. So first is that it can distinguish non-isomorphic graphs, and suddenly the problem of over-smoothing isn't there anymore, right? Because if you have a non-contrastive RNN, then the directional energy of the activation of the RNN is bounded by its last element or the first element. And of course, you can analytically write down the discovery of a 3-member ring or the existence of 3-member ring. And it also has this theoretical guarantee that the sensitivity or the the gradient of one node embedding with regard to another is not diminishing. Right, so we ended up with this very interesting framework, which I think we will keep developing, and we hope that will be the foundation of many interesting physical modeling applications. So it has such interesting sort of characteristics or advantages. So first of all, we can distinguish a lot more rich graph motifs, for example, a three-member ring. And as you can see here, the duration energy is not decaying anymore, right? We proved that theoretically. You can also show that. So this is the only architecture that can have a non-diminishing duration energy over the time, over the number of layers, even if you have 50 layers. It is even faster than GNN, your most traditional King-Van-Welling GNN GPU. And the reason is that because the RNNs are so aggressively optimized, and we do not enumerate the GC matrix, we do not involve the sparse matrix multiplication, so it's actually a very efficient algorithm. And because it's so stochastic, it's naturally robust to perturbations and to random deletions and alternations. Right, so although I have 4 minutes left, this is all I have, and I'd like to thank all of my collaborators, and especially the students that have been coaching, and I thank all of the funding agencies for the bread and butter, and thank you for your time. Yes?
Yeah. Can I understand your design of the random walk, structural random walk, as a form of kind of, it seems related to sort of like counting different homomorphism, or like,
right.
And it also seems to me that you're doing some sort of symmetry breaking because you want to mark different labels of the
Precisely,
node.
yeah.
And yeah, so can you comment on that, and how does the sort of connect to, say, homomorphism count or like symmetry breaking?
Oh, right. So random walk kernels and the homomorphism counting kernels, they have in many cases similar expressive power. So this is also the case when you translate the kernel into the network. But the only difference is that, of course, this is not a kernel method, so it's more efficient. Right.
How about like symmetry breaking, where I feel like you're now like marking the nodes and then like traverse them in some like particular way.
Right.
And yeah, it seems like another popular heuristic in the literature is to mark some special node on the graph. And
Right.
And then so maybe like canonicalize them in some special way.
Yeah, so there are sort of two classes of related literature. One is that the random perturbation of node embeddings, or random assignment of labels. And the second class is what's that called, the positional encoding, where you assign based on the structure, not just the semantics, right? Well, the only difference is that, so here, I believe that we are the only one who can prove that this can detect any non-isomorphic graph up to the reconstruction conjecture.
I see. So
right.
You can say more like theoretical.
Right, yeah. There are cases where, for many of these related works, you can find edge cases where it cannot distinguish, but as hard as we try, we never found an edge case that can break our isomorphism test. Thanks. Oh, yes. Oh, right, yeah. So.
Also, I think that the delay energy doesn't go down with adding layers of GIN, right?
So two questions. You were asking first about the expressiveness, and second is the over-smoothing behavior. So I would like to explain here that there are tricks you can do pass certain isomorphism tests. So, for example, so here you can hard code the ring size, for example.
I was mentioning, I was talking about
GIN, right? The GIN cannot distinguish this either. Right? You can write it down, right? You don't have to like train any networks. You can write it down, and you realize that without the node to graph communication, you cannot distinguish this. But with that, it's no longer wise for the layman equivalent. But without that, you can analytically write down this. It will render exactly the same expression for both of these graphs. And the comment about oversmoothing is also true. So there are a lot of techniques out there that alleviates oversmoothing, and there are a few common approaches which are benchmarked here. The animation is a bit slow. Sorry. Right. So there are a few techniques that you can do. You can do job patch, which is the perturbation of the graph structure over time. You can also do residual connection, of course, right? So that it will add the distinct, unique embedding from the very beginning to all of your results, which of course helps. And you also have a GCN2, which is empirically very performant architecture where you do this like very small steps of it's basically like ODE. It's like infinite deep GNN, except that it's discretized and it's residual connected, and you also have attention. So there are a lot of tricks. But the problem with all of this is that it doesn't stay there if you have like a truly long or truly deep architecture. But our result shows that as long as you have a non-contrastive RNN, which like by default it's almost true even if you don't constrain it. In our case, we didn't constrain it. Like this, it will stay. The direction energy will stay the same, right? So part of the reason why like GRU and LSTM works is that the activation function is applied to the main thing once. Well, this is basically what happens. Yeah. Thanks.
All right, let's thank the speaker again. Thank you
Thank
very
you.
much.